Hello and welcome, this is Matthew. And today I have a very interesting looking triple integral. Now, this is the first triple integral I have done on this channel. Now, it won't be the last, but very good introduction on this channel to triple integrals. So, yeah, the way this integral was born is because a mathematician got bored. So, what you should take from this story is never let a mathematician get bored. Okay? The reason why is because something like this will happen. So, yeah, just look at this thing. It's big. It's monster. It looks like a monster, man. It just looks like a monster. Okay, so before I hop into this integral, please like and subscribe. It really does help me out. Okay, I'll give you a second to do that. Okay, have you done it? Okay, good. Now, the first thing I want to do is simplify the denominator by factoring it. So let me go ahead and factor it, and I'll be back in a second. Okay, if you remember your algebra skills, you could probably factor this. Okay, so here's the answer right here. Now, if you want to check that this is true, go ahead and multiply it out, and you'll find that it is true. Okay, so now that we've factored the denominator, let's go ahead and replace it. Okay, there we go. Now, before we get any closer to the end, let me say this. I'm going to, skip a couple steps. Well, not skip. I'm going to cut the video so I can, write the integral or something like that. Because I don't want this integral to be like over 25 minutes long. I want to keep it under 20 or under 25. So I'm going to cut a couple times. Like for example, I just cut there to factorize it. Um, yeah, but I'll leave those filler uh, solutions as homework to you. So yeah. Now the second thing I want to do is take all the x terms without a z or a t. So I'm going to take all the x terms out of the third integral and put it into the first integral. So let me do that right now. Okay. Now, for example, that was one of the cuts I just did, but the only reason why I cut is so I could write it out. Now, all I did was take all the x terms without a z or a t into the first integral and leave all the terms with a z or a t inside the third integral. Now, if you've taken Calculus 3, you know that a method of solving triple integrals is separating them all and solving them separately. But in this case, we can't because z and t are dependent on x. So we cannot separate these integrals. Okay, but what we can do is solve the z integral and then the t integral and finish it off with the x integral. Alright, so from here, what I want to do is solve the z integral. So solve it inside out, the triple integral. So I want to solve this integral. Now, what should we call this integral? Well, we'll call it I sub z. I sub z. Now, the next thing I want to do is to define a function I sub z of maybe, just L. L could work. Where this integral, it would equal the integral from 0 to infinity of cosine of Lz divided by z squared plus 1 dz. Now, the reason why I would want to do this is because I want to take the Laplace transform of this integral. Now, I sub z is a pretty famous integral. I've seen a couple YouTubers solve it. I've seen it pop up many different places, including this integral. And my favorite way of solving this integral is by using the Laplace transform. Okay, so I guess I'll define a function I sub z of L as this integral right here, and then I'll take the Laplace transform of it. So let me do that right now. Now, this was a pretty big skip I just did. Let me explain what I did. Well, I said I was going to take the Laplace transform of I sub z of L, and that's exactly what I did. Now, if you don't recall the Laplace transform, well, the Laplace transform of f of t is equal to the integral from 0 to infinity of e to the negative s t and then f of t dt. Okay. Now, the Laplace transform is an integral transform, and usually, or what the Laplace transform does, is it turns a non-algebraic equation into a algebraic equation, so it's easier to solve. Now, typically we use Laplace transforms for differential equations, but they can also sometimes be used to solve integrals like this one. Okay. Now, what we'll do for our Laplace transform of our integral function, we can go ahead and take the z term. Well, actually, first, the big question is, can we change the order of which we integrate? So, can we integrate with respect to L first? That's the question. Well, so what we need to do is change the order of integration, but can we do it? Well, we can use Fubini's theorem to do that. And in this case, Fubini's theorem works. So we can go ahead and interchange the way we integrate. So we can integrate with respect to z first, or we can integrate with respect to L first. But the most helpful will be integrating with respect to L first. So, since Fubini's theorem works here, let's go ahead and do that. So, we'll integrate with respect to L, and then z. There we go. Now, the second thing I want to do is take the z terms into the first integral. So the ones with only z. So we won't take the cosine because there's an L, but we will take the z term. So let me do that real quick. Here we go. Now all I did was take the z terms without an L into the first integral and keep the z terms with an L inside the second integral. Now the integral with respect to L, if we recall the Laplace transform, which I just had that down, this integral would be equal to the Laplace transform of cosine of Lz, where in this case, z would be a constant because we're integrating with respect to L. Now, the way we can solve this integral is by using the Euler's formula and taking the real part of it. We can do that, or we can look up our table of Laplace transforms and solve this. Now, if you look up your table of Laplace transforms, you'll find yourself at this answer. S divided by s squared plus z squared. There we go. So the integral with respect to L is equal to s divided by s squared plus plus z squared. So there we go. Let's go ahead and apply this to our integral. Let me go ahead and put this down. There we go. I went ahead and wrote it down. So the first thing we can do with this integral is take out the s term outside of the integral. There we go. And then the way we solve this integral is by using a partial fraction decomposition. Now, I won't give an introduction to partial fraction decomposition in this video, but if you want to see an introduction to partial fraction decomposition, please leave a comment. And also, leave a comment on if my videos are clear and if I'm easy to understand. Because if I'm not, I can, fix what I'm doing wrong, and then the videos will be easier to watch. Okay, so let's do that partial fraction decomposition real quick. The whole idea of doing this partial fraction decomposition is by turning this one big fraction into two separate easier fractions. So that's exactly what I'm going to do here. So the way we can find a is by multiplying the numerator of the left-hand side by the denominator, so s squared plus 1 times z squared plus 1 times s squared plus z squared. There we go. Now, on the left-hand side, we see a cancelization. We see this goes to 1. So, delete, this goes to 1. And if we multiply the right-hand side with the exact same thing, you'll find yourself... Sorry about that. Didn't mean to paste, meant to delete. With a times s squared plus z squared plus b times 1 plus z squared. There we go. Now all we did was multiply the denominator to the numerator on the left-hand side and right-hand side. Okay. Now to find a and b, multiply the terms out, and then, match the terms on the left-hand side and right-hand side, and then solve for a and b. And if you do that correctly, you'll find yourself at this answer. There we go. So here is the answer for the partial fraction decomposition. Now, we simplified our integral into two separate integrals instead of one big hard one. Now we can go ahead and solve these integrals easier. So let's do that. Now here's our new representation for the Laplace transform of I sub z of L. Here we go. Now what I did from the last cut, I went ahead and factored out the 1 over s squared minus 1 right here outside of both integrals. Since a and b both had it inside of them, I went ahead and factored it out of both integrals. And this s in the numerator of s squared minus 1 was from the previous integral. We had it outside. So it was just a multiplying term outside. So it's still there. Okay. Now, these two integrals are actually pretty easy. You can go ahead and use the inverse tangent or the arctangent if you prefer. Yeah, I'll leave the terms out. I'll leave them as homework for you. But if you solve both of these integrals, the first one should be pi over 2. And the second one should be pi divided by 2s. There we go. So here we go. Now, let's go ahead and factor out the pi over 2 and then multiply the terms. Let me do that real quick. There we go. I went ahead and multiplied all of the terms. And here we go. Now, we have the Laplace transform of I sub z of L. Now, our goal is to have just I sub z of L. So what we need to do is take the inverse Laplace transform of both sides. So let me go ahead and do that real quick and explain it. Now, all I did from the last cut was take the inverse Laplace transform to both sides of the equation. Now, if you look up your table of inverse Laplace transforms, you'll find that the first inverse Laplace transform is equal to the hyperbolic cosine of the L, because remember, we went from L to S, and then S back to L. Okay? And the second one will be the hyperbolic sine. So it will be the hyperbolic sine of L. There we go. Now, the hyperbolic cosine of L minus the hyperbolic sine of L minus is equal, if we recall, is equal to 1 over e to the L. Or if you prefer, e to the negative L. But I prefer writing it as this way. Or this way. Yeah, I prefer writing it this way. I keep misspeaking. I am talking too quick. I am sorry about that. And also, another point. If I am talking too quick or going too quick, please leave a comment down below. And if you prefer longer videos or shorter videos, please comment down below. And I can release a uncut version of this video. So it'll be longer, but I will be explaining maybe a little bit better. Okay, so now the I sub z of L is equal to pi divided by 2 times e to the L. There we go. So, we have now solved I sub z of L, but that's not the exact same integral as what we started with, I sub z. Well, if we observe I sub z and I sub z of L, if we replace L with with t times x, we have this integral. We have I sub z. So that's what I'll do. So I sub z is equal to I sub z of t times x. So, which is then equal to pi divided by 2 times e to the t x. There we go. Now let's go ahead and apply this to our integral I. Here we go. Now all I've done is apply our answer to our I integral, the triple integral, which is now a double integral, which is slightly better. Okay, so what we can do, the first thing we can do, is take this pi over 2 outside of the integral. So I now equals pi over 2 times this integral, but now we have to take this one out, and I'll actually write it as e to the negative tx now. dt dx. There we go. Now, this integral is actually pretty easy compared to the last one. It was a little bit of a process. Now, this integral, all you have to do is make the substitution, let u equal t times x, and if you do that properly and solve the integral, it's just a regular improper integral, you'll find yourself at the answer 1 over x. I'll leave the details as homework. Okay. Or solution as homework. Now, that was a pretty easy integral compared to the last one. So let's go ahead and delete it and replace it with the answer. So, there we go. Now, the next thing I want to do is look at the denominator of our integral. We can go ahead and factor out an x to the negative 2. So I have an x to the 4 now, plus 1. And you can go ahead and multiply this out to make sure it's true, but it is. Now, x to the negative 2 in the denominator, well, we can just bring that up. But instead of a negative 2 in the exponent, it will be a positive 2. There we go. Now, one more thing. X squared divided by x is going to be just x. So we have simplified this quite a bit. Okay, there we go. Now, another thing we can do is make a substitution. Let u equal x squared. This implies that du equals 2x dx. Okay, now we see an x dx, but we don't see a 2. We are missing a 2 right here. So let's go ahead and divide it out on this over on du. So therefore, that 2 vanishes, and now we have a match. X dx, x dx. So there we go. No, I mean, now as for our limits, if we let x go to infinity, u will also go to infinity. If we let x go to 0, u will also go to 0. So therefore, our limits are not bothered. But if we also look outside of the integral, we have a pi over 2. So we have a match right here. A 1/2 and a 1/2. So there we go. Now, this right here, this integral, is... Wait a minute, did I confuse myself here? Yes, I did. Okay, my bad. It's going to be a pi over 4. Sorry about that. A pi over 4, not just a pi. I was going to write just pi. I almost made a mistake there. I'm sorry about that. No, we're not going to have just a pi outside. We're going to have a pi over 4. Yes, sorry about that little mistake I almost made. So, times the integral from 0 to infinity. Let me write this out real quick and I'll say what I did. Here we go. Now, all I did was write it out, and here we are. Now, the first thing I want to do to this new integral is simplify the numerator. So the way I would do that is by using Euler's formula. So let me write down Euler's formula real quick. Here is the Euler's formula. Now, if we take the real part of Euler's formula, so the real part of e to the iu, well, that's just going to be equal to cosine of u. There we go. Now, if we had taken the imaginary part of Euler's formula, then we would get the sine function. Pretty cool. Now, what we need to do is replace u with sine of u. So that means the real part of e to the I sine of u is equal to cosine of sine of u. There we go. So let's go ahead and replace the cosine of sine of u with the real part of e to the I sine of u. So let me do that real quick. Okay, now after using Euler's formula, we now have I equals this new looking integral. Now, the next thing I want to do is combine the exponents of e. There we go. And then if we recall Euler's formula, right down here, e to the iu is just our exponent in e. So now we're going to have a tower of e's. So it's going to be e to the iu. Now, the next thing I want to do is use the series representation of e to the u. So let me write that out real quick. Here is the Taylor series representation of e to the u. Now, let's replace u with e to the iu. So on the left-hand side, we'll have an e to the iu, and the right-hand side will have the sum from n equals 0 to infinity of e to the I n u divided by n factorial. Okay, now let's go ahead and apply this to the integral, and I'll explain what I did. Here we go. Now, the big question, can we take the summation outside of the integral? So can we interchange the way we do it? Well, this is a type of Fubini's theorem. If the integral of the sum of the function is convergent, therefore the sum of the integral of the function is convergent. So since this integral does in fact converge, we can go ahead and switch the order of which operators we use first. So we can do the sum first or the integral first. But what would be helpful for us is doing the sum first, doing the integral first and then doing the sum. So let's go ahead and take out the summation outside of the integral because the integral is convergent. Therefore, we can do that. And that's a handful of words, so let's apply this. Now, after applying that, we now have a new representation for I, which is right here. Okay, now, the first thing I want to do is actually take the real part of the numerator. So we're going to go ahead and take the real part. Well, we're going to go ahead and bring in the real part into the integral, and yeah, change the e to the I and u into a cosine. So if we recall Euler's formula, the real part of e to the iu is going to be cosine of u. So in this case, if we let u go to n times u, therefore the real part of e to the I n u is just going to be cosine of n u. There we go. We go ahead and move this over. There we go. Hey, wait a minute. We just did this integral, didn't we? Yes, we did. Right up here, this integral. We called it I sub z of L, but if we let L equal n, there we go. That's the same integral. No matter if we're integrating with respect to z, or all we can do is just make the substitution let u equal 0, but it doesn't matter in this case since it's just a definite integral. So there we go. Now, we basically have the answer. So this right here equals I sub z of n, which then equals pi over 2 times e to the negative n. There we go. Yes, this should be true. Yes. So, now, we can go ahead and bring this pi over 2 outside of the integral and sum. We can bring it out here. So, it'll be a pi squared now, because pi times pi is pi squared. And 4 times 2 is, of course, 8. There we go. So, let's go ahead and replace this integral with e, or let's just put this up here, e to the negative n. But if we recall the sum for e to the x, so e to the x equals the sum, n equals 0 to infinity of x to the n over n factorial. And if we let x equal e to the negative 1, or 1 over e, therefore we'll have e to the negative n. There we go. That is exactly this sum right here. So, let's go ahead and replace this sum with e to the 1 over e. There we go. This is our integral, I. So I is equal to pi squared over 8 times e to the 1 over e. Now this is just a very, very, very satisfying result. Pi's and e's coming together. I mean, it is just beautiful. This integral is one of my favorite integrals I've ever done. It's the first triple integral we've ever done on the channel. So let me go ahead and write this down over here. This right here equals e to the 1 over e times pi squared over 8. I'm so sorry about this. I cannot write an 8 right now. There we go. That took way too long to write that 8. I am very sorry about that, but it's okay. We solved the integral. I is equal to e to the 1 over e times pi squared over 8. Now, like I said, what a beautiful result. I mean, if this doesn't make you love calculus, I don't know what will. I mean, honestly, I really don't. So, if you made it this far into the video, I really appreciate it. Please like and subscribe, and yeah, have a good day. Bye-bye.